All right, so I'm going to try and move through this material a little quickly, but I'm going to break it into two parts because first we're going to consider how we find some kind of heat, Q, produced by a chemical reaction, and then I'm going to do another one about how to find the heat from a physical process. Now we're going to focus on calorimetry. That's the experimental way to find these kind of data. I just want to remind you that what we want to find is a change in energy, where the change in energy is equal to the delta H, or Q, plus the P times delta V. Now, typically, this pressure is held constant in most of these. This represents work. Okay, and we're going to try to eliminate as much work as we possibly can by holding the pressure constant. And even if there is some energy in some of these, they're often not very. It's often not very much. So, for example, we might measure some experiment to have something in the order of 435 kilojoules of heat per mole. The same thing we might find for the energy change, maybe 437 kilojoules per mole. And so even if we can't exactly eliminate all the heat, we can often get very close. And in most cases, we can eliminate a lot of this work. All right, so a few terms. The heat capacity is the amount of energy needed to increase the temperature of a sample by 1 degrees Celsius. The specific heat capacity, which is what we're mostly going to work with here, specific heat capacity, these are values found in the CRC. It's the quantity of energy required to increase the temperature of 1 gram of some substance by 1 degree Celsius, or by 1 degree Kelvin, or 1 Kelvin. And the formula is, for the specific heat capacity, the C is going to be Q divided by mass times the delta T, and we'll do more of this. Likewise, there's another heat capacity. The only real difference is instead of measuring for 1 gram, we measure for 1 mole. Okay, we're still going to raise it by 1 degree. Okay, and it has slightly different units here, which we'll work on in a little while. So heat is dependent on basically three things. The specific heat capacity of some object, which we can find in the CRC. Here are some examples. For example, glass has a specific heat capacity of 0.385 joules per gram per degree Celsius. Iron has one. Copper has one. You know, all kinds of, almost everything's been measured in some manner for that. The one you need to know, okay, which I won't give you if you come across it, is the specific heat capacity of liquid water at 4.184 joules per gram per degree Celsius. It's also dependent on, or the heat is also dependent on the amount. All right, if I have 10 grams of something, I expect to get a proportional amount if I double that amount. And also the change in temperature of the object in degrees Celsius, or K. Now, the main formula here is heat is equal to the mass times the specific heat constant, and I'm just going to say C specific for right now, times temperature final minus temperature initial. Okay, that's important. Now, I want to talk about these units. I guess I'll have to arrange this so I can lift it up some. Okay, I want to talk about the units for just a minute. Okay, so let's go back to the specific heat of units. See, the units of specific heat are joules per gram per degree Celsius. as you can see, for example, right here. I also gave you the same kind of a thing, but with Kelvin, and so I want you to notice that it doesn't matter whether the degrees are in Celsius or Kelvin, or the temperature. But don't convert. Either use one or the other. So don't convert between joules and Kelvin. There's really no reason to. If you do it right, it doesn't hurt anything, but there's no reason to. And why not? Because here's our degrees Celsius scale and our Kelvin scale. All right. If this is 100 and this is 0, this is for water. Okay, water freezes at 0 and it boils at 100 degrees Celsius. Okay, likewise for Kelvin, okay, water is going to freeze at 100. I'm sorry, let me do this right. How about, I don't know, let's look. Oh, here's what I want, 273 and 373. Okay, its boiling point is its freezing point is at 273 Kelvin. 373 K is the boiling point. Notice that on either scale, the difference is 100 degrees or 100. Okay, so a change of 1 degree Celsius is also a change of 1 Kelvin. They're on the same scale. So you don't have to convert anything. If it says degrees Celsius, you can use Kelvin. If it says Kelvin, you can use degrees Celsius. You don't have to change anything. Now, typically, degrees Celsius is how you measure in the lab. Okay, but either scale is fine. Okay, either unit is okay. You don't have to really mess with it much. All right, so what kind of experiment do we typically do? Usually that's going to be a calorimetry experiment. These can be very, very simple. Many labs just have a styrofoam cup of some sort. Whoops. And for example, in this styrofoam cup, you can see that there's a thermometer that's measuring. This is measuring the surroundings for our chemical process usually. All right, and inside is some kind of a sample down here. There's a little stir thing to stir up the solution and make it have an even heat content. And this sample, whatever that chemical is usually the system. The surroundings are the water. Now remember, I told you it's very critical to always identify your surroundings and your system. So let's see how that works in calorimetry. All right, this would be an example of an endothermic experiment. What happens here? We're going to look at how we measure this. If we have an endothermic experiment, the temperature is going to decrease in a chemical reaction. Okay? That means that the system had to absorb heat, bring heat in to complete the reaction. And therefore we have Q greater than 0 or a positive value, and likewise we're going to have a delta H greater than 0. The reason is because the heat energy that is needed to make this reaction go, so to speak, has to come from the surroundings. Likewise, when you have an experiment that's exothermic, again, be sure you label everything. Okay? In this case, the surroundings, this water or whatever it is, are the surroundings. And in this case, like this piece of chemical, whether it's a throat lozenge, which is what it looks like to me, or anything else, is going to be the system. Okay? Now, what happens during the experiment? The temperature of the surroundings increases. Okay? So in other words, the system had to release heat in order for that temperature of your surroundings to increase. And in that case, that means we're losing heat, okay, from the system, and our delta H value is going to be less than 0. One other, which I've kind of brought your attention to before, one other type of measurement that you might see in the lab, instead of being in specific heat units, remember our specific heat is joules per gram per degree Celsius or Kelvin. In the case of a molar heat capacity, we're not talking about 1 gram, but a whole mole. And in that case, our units will be joules per mole per Kelvin, okay, or degree Celsius. And so I showed you on this slide a little example of how to do that. It's the same amount, nothing changed about the specific heat constant, except that the units are different. Okay, so a gram or a mole. Okay, and I'll show you how to work with that. Now, one more thing that you might see in a laboratory is something called a bomb calorimeter. Those are typically not used in a freshman or a early chemical class. But in these cases, what we're measuring here is a constant volume. All right, remember in our other ones we had a constant pressure, but here we have constant volume. This allows us to find, in cases where we can't really get just the heat, we can find the delta E, or the change in energy. Now, in that case, the specific heat of the bomb has to be tested and known. All right, so you have to have some amount for the heat of the bomb. That's part of this equation, where to find the heat instead of the specific heat of the object, we're trying to figure out what the specific heat of the bomb is, and then to find the heat, we'll take the C for that bomb times delta T. So every bomb has to be experimentally determined for what that specific heat is in order to get a good calibration, get good results. Okay, so in this case, the system is whatever the compound is and some oxygen, okay, some oxygen, and the surroundings are the water and the bomb, okay, so everything, including the water and the calorimeter. In most of what we're going to be doing, we don't really take into account the calorimeter, the styrofoam cup, because we don't really need it when we're just doing constant volume, constant pressure. So, some examples. What do I do with my first one? Here we go. All right, we're going to calculate Q when 28.6 grams of water is heated from 22 degrees to 73 degrees. All right, so we want Q. So we have information that tells us the mass. We can find the specific heat. Okay, so specific mass times specific heat times the change in temperature. All right, now this change in temperature, the way you set this up is critical. Okay, that determines your sign. And so it's not really the best to do that. Instead, you should use temperature final minus temperature initial. It always should be set up in that order. Okay, and you ought to get this straight before you get started. Okay, so our initial temperature is 22 degrees Celsius, and our final temperature is 78.3 degrees Celsius. Now this matters because the sign is important, and you're going to know the sign by knowing what these, by setting up this equation properly. Okay. So, in this case, we're going to take 28.6 grams of water. Okay, and we know the specific heat capacity of water is 4.184 joules per gram per degree Celsius. And in this case, we'll have 78.3 minus 22.0. Both of those are degrees Celsius. And Q works out to be equal to 67.40 joules. Okay, now, no, I guess that's it. 67.40 joules. Let me just assume for just 1 minute, okay, that instead of starting at 22 and ending at 78.3, I do the other way around. I start at 78.3 and I end at 22. Okay, so in this case, what I'm setting up here is my temperature initial in this case is 78.3 degrees Celsius, and my temperature final is 22.0 degrees Celsius. Now, I want you to see the difference it makes. Now I've got 28.6 grams times 4.184 joules gram degrees Celsius times 22.0 minus 78.3, and when you calculate this up, Q works out to be equal to negative 67.40. And so this sign is critical. In this case, it's a presumed or an assumed or an implied positive value, and here we have a negative value. And that matters because we have to decide things like exothermic and endothermic, and are we gaining or losing energy, etc. Sorry about that. Let's see, what's the specific heat capacity of silicon? If it takes 0.192 kilojoules to raise 45 grams by 6 degrees. Okay, so what we're looking for is the specific heat capacity. So we'll use Q is equal to MC delta T, but in this case we want specific heat. So C rearranged would be Q divided by the mass and delta T. All right, so let's see. We raised temperature by 6 degrees, so that's going to be a plus 6 degrees Celsius for our delta T. So in this case, we'll have, and also, do I like these units in kilojoules for my heat? And the answer is no, because the units of specific heat are joules per gram per degree Celsius. And so kilojoules is not what I want, but 0.192 kilojoules times 1,000 joules per kilojoule means that this is equal to 192 joules of heat, 192. So to find my specific heat capacity, I'll do 192 joules divided by my mass. The mass in this case is 45 grams. So 45 grams of the silicon times the change in temperature, which we determined was a positive 6 degrees Celsius. And this works out to be equal to 0.711 joules gram Kelvin, or degrees Celsius. All right, let's go one step further on that. And instead of having the units in joules per gram per degree Celsius, let's do the molar heat capacity. Okay, once we know this value, the specific heat capacity, then we can take the specific heat capacity times grams per mole. Okay, that's going to be our molar mass for whatever object we're thinking of. Okay, so the molar mass of that, in this case, this is going to be 0.711 joules grams per Kelvin times, and then I look up the molar mass of silicon, and that's 28.09 grams for every mole of the silicon, which is what we're interested in. And this works out to be equal to 20.0 joules mole times Kelvin, or degrees Celsius. All right, now let's look at a candle. We want to know, some candle, we've got a bunch of information, and what's our question? How much heat is released from the candle? All right, so let's evaluate our information. We've got a candle. We know its mass, or we can find it out because it's the formula is given to us. So we'll take 28 times 12.01 and 58 times 1.008. This works out to be equal to 394.74 grams per mole. We know the mass of water. Hopefully you have that memorized by now, but just in case you don't, there's that. So next we need to know the mass of the candle. Okay, so the mass of the candle is going to be equal to that we used. The mass of the candle that we used, we can just take a positive value here, 32.48 grams minus 31.22 grams. And so the mass of that candle is 1.26 grams. We also have the mass of the water, okay, and that's 400 grams. Okay, so far we have the specific heat of, we don't have our specific heat. Well, we have our masses. And so the specific heat of water we know is 4.184 joules grams Kelvin. And then we think about what our specific heat for the candle is, and we look through all this information. We don't have that memorized. We don't have a CRC available to us. There's just no information on that, so we don't know what the specific heat of the candle is. We can find the change in temperature. Let's start with this one. The change in temperature for the water, all right, is going to be from 10 to 40 degrees. Okay, so that's 40 minus 10 gives us 30-degree change, and that's a positive value. What about the change in temperature of the candle? Well, we have no information about that in this problem. It doesn't tell us what the temperature was at the beginning. We might be able to assume that it's at room temperature, which is 25 degrees Celsius. I mean, that's probably an okay assumption, but how do we know what the final temperature is? We're not really sure, right? So we can't really calculate the change in temperature here, or the change, or the specific heat constant. So how do we go about figuring out how this works? Well, this is our, by the way, should have done this first. This is our system, and this is our surroundings. If we know everything we need to know about the surroundings, like we seem to know here, then we can figure out what happened in the system. All right, so we have a mass, a specific heat, and a change in temperature for the water, but we seem to be missing that information for the candle. But we can nevertheless find our Q. Okay, if we know Q of the surroundings, we're also going to know Q of the system. Okay, because Q of the surroundings is the negative Q of the system. So we'll find the Q of the surroundings, and all we have to do is change the sign for the system. So in this case, Q is going to be equal to 400 grams times 4.184 joules grams degrees Celsius times our temperature change of 30 degrees Celsius. And so Q for the water, okay, for the surroundings, okay, it's not really around it, but that's what we measured it. We'll call it the surroundings. Works out to be equal to 50208 joules. Whoops, joules. All right, so now we have the heat that changes during the reaction. In this case, it's a positive heat because the water increased in temperature, and the water is the surroundings. But once we know the Q of the surroundings, we also know that we have the Q of our candle. That's our system. Q of the system. Also, we might call that Q of the reaction. Okay, all of that's going to be equal to negative 50,208 joules, just the opposite of the surroundings. So this is our system, has the same value as the surroundings, but the opposite sign. So that is how much heat is released from the candle. Okay, that's Q. What if I also ask you to tell me what the delta H of this reaction is, which I could. Okay, so now let's go in here and let's think about what delta H of our reaction is. I'm going to put that at standard temperature, which we'll look at in a little while, or standard conditions, and we'll look at that in a little while. Now, what do I know about this reaction? Well, first I'm going to change these to kilojoules. I know that Q is equal to, let's just say negative 50 kilojoules to make life easy. Okay. I also know that I had a mass for the candle of 1.26 grams. And what else do I know? And I know the molar mass of the candle. All right, so in order to do this, I'm going to set up delta H of my reaction is going to be Q divided by the grams of the system times the molar mass in grams per mole. Oops. Clean that up a little bit. The molar mass. And I'm going to use grams per mole. So I'm going to have the top with the grams and the bottom with the moles. So in our particular case, in this candle, we've got minus 50 kilojoules. When we did this reaction, we started or we used 1.26 grams of the candle. Okay, so I'm going to write system here just to help you see it. 1.26 grams of the system. And then I'm going to use the molar mass of the candle, which is 394.74 grams for every mole of C28H58 or whatever that was. When I get done here, this is going to be equal to 15,000, roughly six, I'll just round it, 16. Oops. It's going to be equal to 15,279 kilojoules per mole. Now, did I do that right? No, I did not do this right. Why not? Because I didn't bring my negative sign with me. Okay, so this has to be a negative 15,200 or 729 kilojoules. Oh, it's 729. which is why I should have said minus 16 to begin with, kilojoules, 16,000. That's just rounded, okay? But anyway, I transpose those numbers. Hopefully that's not a problem. Anyway, that's how you find the delta H of the reaction. All right, so be sure you bring any negative sign, whatever the sign is. Once you've found the Q of the reaction, which we did over here, you're going to bring that negative sign everywhere you go. All right, so in this problem, we've got a sample of some kind of metal. It's hot. Then we're going to place it into some cool water, okay? And we're going to determine the final temperature. The final temperature. And so, and I gave you the specific heat capacity of the nickel here. So this is a distribution problem where you're going to have temperature final on two sides of the equation. All right, so you're going to have to do a lot of math here, but it shouldn't be too difficult. All right, so in this case, let's think about the conservation of energy reaction, or a theory that says that the metal, whatever happens in the metal, plus the Q of the H2O, overall that's going to be a total conservation of energy 0. In other words, the negative Q of the metal is also equal to the Q of the H2O. Now, I chose the metal, okay? I could have done this either way, but I chose the metal to go down in temperature, to be a negative sign, because the temperature is going to go down. Okay, we're starting high, we're putting it in something cool, the heat's going to transfer into the cool thing, and so I'm going to expect the temperature of the nickel to go down. All right, which so therefore I want this to be a negative value. The negative value gives me, in the end, a positive value, but let me show you that. So we're going to take this lovely formula where we're going to do MC delta T for the water, and that's going to be is equal to negative MC delta T for the nickel. Now, we know everything in this reaction except the temperature final. We've got to find our final temperature, and so we're still not quite done with setting up our reaction. Let's go up here. We'll do the water first. 100 grams of H2O. Now, we're assuming for the moment that, no, even though this isn't correct because density varies, but to make our life easier, we're going to say 1 gram of water is equal to 1 mil of water. Okay, at 25 degrees, that would be true, but at 23 or 22 or whatever we're at here, it would be slightly different. But we're just going to assume that it's 1 gram per mil. 100 grams of H2O times 4.184 joules gram degrees Celsius times the temperature final, which I don't know, but I do know what temperature it started at, which was 22 degrees. 22. I'm going to set all this equal to, and I should have written smaller, so I'll write down here a little bit, all this equal to negative, which I'm bringing along with me, 275 grams of nickel times the specific heat of nickel, 0.444 joules gram degrees Celsius, times the temperature final, I don't know, minus 100 degrees Celsius. Okay, so this is the expanded view, and you're going to need it. You really do. Now, the next thing I'm going to do is set this up so that I have a value here and a value here. All right, so therefore, if I multiply 100 grams times 4.184, I end up getting 418.4. Now, I got rid of my grams up here, so this is joules per degree Celsius, okay, because I already canceled out those grams. And then I'm going to have times temperature final minus 22. All that's going to be equal to these two multiplied together. So that's going to be negative 122 joules per degree Celsius, because I multiplied out the grams here, times temperature final minus 100 degrees Celsius. Okay, and remember, I'm bringing my negative sign down with me. All right, so what I'm going to do now is I'm going to multiply, I'm going to distribute some more. So I'm going to distribute this to this, and likewise on the other side. And that's going to give me 418.4 joules per degree Celsius times my temperature final, okay, when I multiply these two, minus, now I'm going to multiply this times the 22 degrees, and that gives me minus 9205 joules. Okay, when I multiply times degrees Celsius over here, all I have left is the energy unit. Okay, so just a joule. Here we have a joule per degree Celsius. All that's going to be equal to, now I'm going to multiply this across and distribute, and multiply this across and distribute, and that works out to be equal to negative 122 joules per degree Celsius times temperature final, okay? And then notice here that I've got a negative times a negative. That's going to end up being a positive 12,210 joules. Okay, we're almost there. Now we have on our in our distribution, we have a joule per degree Celsius and a joule per degree Celsius. Both of them were multiplied by a factor of temperature final. We have a unit of a joule and a joule. So I'm going to rearrange this equation and put things on the same side. So in this case, I'm going to add 122 blah blah to both sides. And I'm going to add 9,205 to both sides. Put my units there. So when you rearrange this, this works out to be 540.4 joules per degree Celsius times the temperature final is equal to, and in this case, 21,415 joules. Now, to find the final temperature, I'm going to divide everything by 540.4 joules degree Celsius. 540, 0.4 joules degrees Celsius. The temperature final, okay, is going to end up being, now let's look at what happens to the units here. This is going to end up being dropped on the joules, and the degrees Celsius is going to be the final unit, okay, at the top, because a division divided by a division flips that bottom one to the top, and this turns out to be equal to 39.6 degrees Celsius. So in this case, both the nickel and the water come to the same temperature. Okay, that same final temperature for both of them is 39.6 degrees Celsius. Okay, one more problem. This problem is how you deal with the Q of the reaction, okay, which you'll see lots of. And in this case, we're going to mix two things together, and then we're going to determine the delta H. So in this case, we're going to take 2.53 mils of sodium hydroxide. We're going to add it to 100 grams of some acid, okay? Everything's at 20 degrees to begin with. And we know what the final temperature is. Now, everything is happening in one container here, okay? So, one container. So, the final temperature is 22.5, and we're going to calculate the Q of the reaction and eventually the delta H of the reaction, or the enthalpy. So, to do this formula, you're still going to use Q is equal to MC delta T, okay, but this is for a total mass. The total mass, so the water and the sodium hydroxide in this case. We don't really have a specific heat for sodium hydroxide in here, but most of this is water, okay, and it's in an aqueous solution, so we're going to assume that it has the specific heat of water here, and we also know our delta T. Delta T in this case is going to be equal to the final 22.5 minus 20.0 to the initial, so this is going to be equal to 2.5 degrees Celsius. All right. So let's input our information. We have a total mass of 102.53 grams because we're adding the sodium hydroxide and the water together. We're going to use 4.184 joules, grams times Kelvin, times our temperature change of 2.5 degrees Celsius. Does it matter, okay, that we are in Kelvin here, and degrees Celsius here? No, because the change in Kelvin is equal to the change in the degrees Celsius, so we don't have to mess with anything there. So, now what is this Q? This is a Q for the solution, okay, the Q of the solution. Now that means we put everything together and we measure the solution. And in this case, the Q of the solution works out to be 1,072 joules. All right, but that's not getting us to the Q of the reaction. All right, but because I know that if anything happens to in one direction, it's got to have the exact same value but the opposite sign. So I know that the Q of the reaction in this case is negative 1072 joules. Okay, I know that because of the conservation of energy law. If one gains 1,000 joules, the other has to lose 1,000 joules. All right, so there's the Q. This is the first answer. Calculate Q of the reaction. I have to be the one to change the sign here. What about calculating our delta H? We want to know the delta H of the reaction. Okay, I don't care about the solution. In this case, I'm going to take, to find delta H of reaction, I'm going to take the Q of the reaction divided by the mass of the reaction, the mass of the system, let's say system, times the molar mass. All right, that's going to give me delta H. So, in this case, I'm going to take negative 1,072 joules. Let me put this up a little. The amount of the sodium hydroxide that we actually used in this reaction was 2.53 grams of sodium hydroxide. And then I'm going to multiply times the molar mass of sodium hydroxide, which is rounded 40 grams sodium hydroxide for every mole. Let's look at our units. I'm going to be dropping out grams. I'm going to end up with joules per mole. Well, delta H is almost always in kilojoules per mole, but that's easy fix. All right, so we'll do that later. So in this case, I've got the answer here is basically 16,955 joules per mole. I'm going to say 17.0 kilojoules per mole. Have I done that right? No, I didn't bring my negative sign down with me. I got to have that. So for the heat of this reaction, or the enthalpy of this reaction, I'm going to lose 17 kilojoules per mole, or release that much heat every time I do that reaction, which is an exothermic reaction, right? All right, so I'm going to pick up this a little bit more with the physical changes that we're going to be measuring in the next lesson.